Yeah, so this talk is going to be about a ground state energy estimation algorithm that is designed for the early fault tolerant setting. So in this setting, we assume we have some error correction capacity, but we haven't fully reached this fully error tolerant regime yet. So yeah, so this is kind of an intermediate regime between NISC and the fully fault tolerant. And our algorithm has the nice feature that it achieves the optimal Heisenberg-limited precision scaling. So yeah, so this is a joint work with my advisor Ling Ling at UC Berkeley, and here is the archive number of our paper. Yeah, so at this point, quantum supremacy has been demonstrated in 2 separate experiments, and the natural next question might be for us to consider whether we can demonstrate any useful quantum advantage. And people are particularly hopeful of doing this in the setting of quantum chemistry. So in quantum chemistry, we study Hamiltonians that are of this form. So previous speakers have explained this thing extensively, so I don't really need to go into details. So basically, we have this fermionic Hamiltonian describing the motion of electrons. So we have a non-interacting part and interacting part where this interaction corresponds to Coulomb interaction between electrons. So extensive work has been done to perform Hamiltonian simulation e to the minus IHT ever since this seminal work by Seth Lloyd in 1996. And over the years, many algorithms have been developed to solve this simulation problem. So first, people consider Trotter and the Taylor series, qubitization, etc. And the state-of-the-art algorithms have reached a kind of complexity scaling that is that almost matches the lower bound. So we cannot really improve the scaling substantially. However, only being able to simulate this time evolution isn't enough for us to claim quantum advantage. So we need to answer the question of what classical output can we get out of it. So we're looking for a classical output that can be generated from a quantum computer that is useful and at the same time difficult for a classical computer. And in this talk, we will explore the option of using ground state energy as an output of this kind. So ground state energy is definitely useful. It's useful in predicting material structures, simulating chemical reactions, etc. And it is difficult on the classical side because we don't have a provably efficient classical algorithm to get to chemical accuracy for strongly correlated systems. However, this problem in its original form might be too hard even for a quantum computer. This is because we know that without additional assumptions, this problem is extremely hard. So there isn't much hope of solving this problem in polynomial time on a quantum computer either. So in order to make this problem tractable, what we do is that we introduce initial guess. So we assume we can efficiently prepare state rho such that the overlap between rho and the ground state is lower bounded by some parameter eta. So here eta is assumed to be some known parameter, and the overlap is measured by this quantity trace rho times pi 0, where pi 0 is the ground state projection operator of H. So by efficient, I mean that we should be able to prepare this state rho in polynomial time. And we say that rho is a good initial guess if eta is large. So I'm being kind of vague here because depending on the context, we'll have different criteria for how large is large. So in a complexity theoretical context and in a practical context, we will have different criteria. Yeah, so I'll just say vaguely that it needs to be large. And candidates for this rho include the Hartree-Fock state and also the quantum state you can prepare using variational quantum eigensolver or QAOA. So there is a caveat here, which is we do not have a guarantee for the overlap, but empirically for medium-sized quantum chemistry systems, the overlap is usually acceptable. So basically for the kind of quantum system the previous speaker talked about, there is usually a pretty decent overlap between the Hartree-Fock state and the ground state. And also this paper explored a lot of chemistry systems and computed this overlap. So empirically, we think this could be something that we can use, but there is no theoretical guarantee. So now we have introduced an assumption. So let's first explore the complexity theoretical implication of this assumption. So here we consider a case where this eta is scales like a 1 over poly n, where n is the system size. So the assumption of a good initial guess makes the problem easier on the quantum side. So once we have an overlap of this magnitude, then we can simply run quantum phase estimation using this initial guess, and then this will give us the ground state energy in polynomial time, if the goal is to reach inverse polynomial precision. However, this might not be the most efficient thing to do, which is what I'm going to talk about for the rest of my talk. But the point here is that this problem can be solved in polynomial time, so it is in the complexity class BQP. So it's easier on the quantum side. Does it make it too easy so that a classical computer can solve it too? So we have a kind of an answer to this question in the negative, because this problem is shown to be BQP complete in this recent paper by the following two authors. So this means that if a classical computer given a good initial guess can estimate the ground state energy to inverse polynomial precision in polynomial time, then BQP would be equal to BPP, which is the class of problems you can solve on a classical computer efficiently. So this in turn means that if this is true, then all the for any output distribution of a quantum circuit, you can efficiently sample from it on a classical computer. So this rules out any hope of getting any kind of quantum advantage. Because of this, most people would think that BQP is not equal to BPP, and therefore we still have a kind of like a complexity theoretical guarantee that this problem is hard classically. So now we have established that this is a problem that is useful, that can be solved on a quantum computer, and is classically hard. So now let's look at like some algorithms to solve this problem on the quantum side. So the first algorithm we look at is just quantum phase estimation. So in quantum phase estimation, we run control the time evolution on this initial state rho. So this rho is the initial guess I mentioned, so the time evolution is controlled on this ancilla register. So after we run all these control time evolution, we perform an inverse quantum Fourier transform and read out the energy. So if we look at the total runtime, it will scale as this eta to the -2 times epsilon inverse. So eta is the initial overlap I introduced in the previous slides, and epsilon is the precision we want to get. So let's focus on this epsilon inverse scaling. So this is actually the optimal scaling you can possibly get for the generic case, and it is called the Heisenberg-limited precision scaling. So this is actually a pretty nice scaling. And if we, so this is the total runtime. Basically, you need to run this quantum circuit multiple times. And we have another criteria for judging how hard this problem is, which is the circuit depth. So, so here we need to run time evolution coherently for a length of time that scales like eta inverse times epsilon inverse. So this is basically how large your circuit depth needs to be. And also this algorithm requires multiple control qubits, as can be seen here. So the number of ancilla qubits you use needs to be increased if you want to get increased precision. And basically, this talk will be about a new algorithm that improves upon these criteria. So we propose an algorithm with the following three goals in mind. First, we want to preserve the Heisenberg-limited precision scaling, which is a nice feature of quantum phase estimation. And we want to reduce the number of ancilla qubits. So in our algorithm, we are able to use at most one ancilla qubit, as opposed to like a number of ancilla qubits that needs to increase as you increase the precision. A third criteria is that we want to use lower circuit depths. So the circuit depths we were able to achieve scales like epsilon inverse up to a polylog factor. So this can be compared with the circuit depths required for quantum phase estimation, which is like you have this eta inverse multiplied to epsilon inverse. And in our case, this eta inverse goes into the polylog factor, so that this is a improvement if eta is not too large. So these features are desirable for implementation on early fault-tolerant quantum computer because in this specific setting, we imagine that the number of qubits might be limited, so you don't really want to use a lot of qubits just for this ancilla register. Also, the circuit depth is restricted by the decoherence. So basically, you might even want to have a kind of trade-off between circuit depth and the total runtime. You might want to reduce the circuit depth even at the expense of the total runtime. So these are the considerations we have in mind when designing this algorithm. And for these three goals, we can look at all the existing quantum algorithms for estimating the ground state energy and see if each of them can satisfy all three requirements. And it turns out that our algorithm is actually the only one that satisfies all three. And so there is this quantum phase estimation, or iterative quantum phase estimation, but it needs an exact eigenstate, which isn't generally available. So in this sense, we say our algorithm is ideal for the early fault-tolerant setting. So our algorithm uses a simplified circuit that looks like this. So it requires only a single ancilla qubit. And this is actually the same circuit used in Kitaev's algorithm, which is also known as iterative quantum phase estimation. And in this circuit, we need to choose this gate W depending on what kind of output we want to get. So when we choose this W to be identity, we denote the measurement outcome, which takes value plus or minus 1 by X. And when we choose W to be the inverse phase gate, we denote the outcome by Y. So conditional on this J being chosen as some fixed value, the expectation value of X here will be the real part of the expectation value of this unitary. The rho here is the initial guess we have. And the conditional on J, the expectation value of Y will be the imaginary part. So one thing we can do is just to do Monte Carlo sampling and estimate all these quantities for J equal to 1, 2, 3, all the way to D. And with these quantities, with this data, we will be able to do statistical inference, and this will tell us like a ground state energy estimate. So this was done in this 2019 paper by Soma. However, I want to emphasize that we are not doing this in our algorithm. The reason is that let's first get a very rough estimate of the complexity of taking this approach. So if we estimate all these quantities for J equal to 1, 2, all the way to D, then let's compute the total evolution time required. So let's not worry about what precision we want to get at the beginning. Let's just say we run each time evolution just only once. And then the total evolution time will be tau plus 2 tau plus all the way to D tau. And in the end, you will get something like a D squared times tau up to a 1/2 factor. So we will need to choose tau times D to scale as epsilon inverse. And this results in a tau inverse times epsilon to the minus 2 total evolution time. So I want to draw your attention to this epsilon to the minus 2 scaling, which is quadratically worse than epsilon inverse scaling in quantum phase estimation. So if we take this approach, even if we don't consider any precision requirement, from the simple analysis, we already know that we cannot saturate the Heisenberg limit. Therefore, we need to take a different approach, which is what we do is we sample J from a distribution using the idea of importance sampling. So basically, some J's are more important than others, and therefore we sample them with larger probability. However, what we do is not exactly importance sampling because we will not be estimating these quantities. Rather, we will be designing a new random variable whose expectation value directly tells us what we want to get. So what we do is we introduce random evolution time. So from our previous definition of random variables x and y, we define new variable z, which is x plus I, y. So it takes value within this set plus minus 1, plus minus I, and conditional on j, the expectation value of z will be just the expectation value of this unitary operator. And now let's set j to be a random variable. So we can look at the expectation value of z multiplied to a phase factor. And we just expand the whole thing using the law of total probability. And what we get here is actually a Fourier series of this variable x. So just look at here. So this whole thing, we just look at it as some kind of coefficient. And here we have an extra phase factor e to I theta j. And we have this term e to the ijx. So these are Fourier modes. So this whole thing is actually a finite sum of Fourier modes. And we view this as a function of real valued variable x. So for a function of f of w that can be written as a finite Fourier sum, if the coefficients add up to 1, we can just choose the probability distribution according to the coefficients, and we choose those angles according to the arguments of the coefficients. And then the expectation value of the z times the phase factor will give us the trace of rho times f of x minus tau h. So this, so here we have a kind of compact expression for this expectation value, but it might not be clear to all of you what this means. So this I will explain later. But at this moment, let me just emphasize we can. So this expectation value can be evaluated using Monte-Carlo sampling. Also, a very important feature is that we do not need to resample for each x. So we just generate a bunch of z samples, and they can be combined linearly for different values of x. And so with a finite number of samples, we will have actually a curve rather than a single data point. So this whole thing will be just a continuous function of x. And if a function f can be approximated by a finite Fourier sum, then this quantity can be approximately computed using this method up to an approximation error. Let's consider a specific f, which is the Heaviside function. So here f of w is equal to 1 if w is greater than or equal to 0. It's 0 when w is smaller than 0. And we introduce the eigendecomposition of h. So h is equal to the sum of lambda k times pi k, where lambda k's are the eigenvalues, pi k's are the projection operators into the eigensubspaces. And we introduce this pk to be traced pi k rho, which is the population of the initial state rho in the k's eigensubspace. So yeah, I have to introduce some notations here for what I'm about to say later to make sense. So now let's consider plugging this Heaviside function f into this quantity we had before. So this c of x is defined as trace rho f of x minus tau h, where this f is the Heaviside function. So using the eigendecomposition of h, we can actually write it out in a simpler form. So this is the sum of all the pk such that for all the k such that tau lambda k is smaller than or equal to x. So this is actually a cumulative distribution function of the spectral measure. So what I mean here is that imagine you perform an exact energy measurement used on this Hamiltonian, you will get an energy value as a random variable. So what c of x tells you is that how large the probability is of having an output that takes value smaller than or equal to x. So this is why I call this the cumulative distribution function of the spectral measure. And the reason why we should study this function is that this is a discontinuous function, and each jump of this discontinuous function corresponds to an eigenvalue. So just imagine you have an x that is moving from the left of some k to the right of some k, and as you cross this lambda k, there will be a jump of that takes you from some value to this value plus pk, and therefore all these discontinuities will tell you where the eigenvalues are. So as you can imagine, this is definitely useful for estimating the ground state energy because we are just looking for the lowest eigenvalue. Yeah, and the caveat is that this is a discontinuous function, so approximating it might require some work, which I'll talk about later. So let's first get a sense of what we're trying to do here. So this orange curve here is the exact CDF. So each jump corresponds to an eigenvalue of the Hamiltonian. And using our sampling approach, like constructing this, sampling this random variable z and this phase vector, we'll be able to numerically compute a approximation to it, which we call the approximate cumulative distribution function, or approximate CDF. It's denoted by this g bar of x, and it's shown here on the blue line. So as you can see, although there is significant statistical noise, it's just jumping around, but it, overall, it follows the exact CDF very closely. And most importantly, at the eigenvalues here and here, you can see that the jump almost matches exactly. So, and this is why we can estimate like eigenvalues using this method. So let's zoom in around this actually, this is the ground state energy marked out by this dashed right line. So let's just zoom in around here, and what we will see is, so here the exact CDF function, CDF takes a jump. The height is lower bounded by eta, where so this corresponds to the initial overlap, and because of our assumption, it is lower bounded by eta. And our numerical approximation basically follows it to take a jump, but for the exact CDF, the jump just occurs suddenly because it's a discontinuous function. We're approximating it using a continuous function, so there has to be a transition interval from 0 to beyond this eta. So, and the length of this transition interval we denote by delta. This roughly corresponds to the resolution of our method. So let's summarize how this method works. First, on a classical computer, we sample a bunch of JKs, and we feed them into the quantum circuit to determine how long we want to run the time evolution. After we run the quantum circuit, we perform measurement and get a bunch of samples zk, and then we collect those zk's and feed them back into the classical computer. The classical computer combines both jk and zk, and it will tell us this approximate CDF, which is this blue curve here. So, and then from this approximate CDF, we will get to the ground state energy. Yeah, so using this approach, if we want to get the ground state energy, we only need to find the first jump in the CDF. And this can be done using a binary search. Actually, from the previous slides, you can probably just locate it using your eyes, right? But in order to get to a required precision, we need some more refined approach, which is a binary search. And the transition length delta needs to be chosen to be tau times epsilon, where tau is roughly the inverse of the Hamiltonian norm, and epsilon is the precision you want to get. The max evolution time scales like a tau over delta, which is like an epsilon inverse. So this corresponds to the circuit depth requirement. So basically, our circuit depth is epsilon inverse up to a polylog factor. So this should be compared with the epsilon inverse times eta inverse circuit depth requirement for quantum phase estimation. So here we have a lower circuit depth requirement. And in order to resolve this jump, we need to keep the statistical noise to be roughly below eta, where this eta is the initial overlap. So we need this kind of Monte Carlo accuracy, and the number of samples needed will therefore scale like eta to the -2. And if we look at total evolution time, it will scale like eta inverse times, epsilon inverse times eta to the -2. And this is basically the same asymptotic scaling as in quantum phase estimation. And we have this epsilon inverse dependence, and therefore we have the optimal Heisenberg-limited precision scaling. Now, we also, so besides this theoretical comparison, we also did some numerical experiments. So here we specifically consider a case in which the overlap is diminishing. So this P0 actually corresponds to eta in our previous slides. So we just let this P0 go to 0 and then see with fixed circuit depths, how does our algorithm perform and how does quantum phase estimation perform. So you can we look at the average error of estimating the ground state energy, and as you can see here, this red curve shows how our method performs. You can see as we decrease this initial overlap, our method has a consistently low average error. But if we fix the circuit depth and run quantum phase estimation, the average error just goes up. And actually, in quantum phase estimation, you can keep the error down, but you have to increase the circuit depth in order to achieve this. So this is what is shown in the green curve. So here we just increase the circuit depth as we decrease P0, and we're still able to achieve a low average error, but the circuit depth is growing. So the same thing can be seen if we look at the failure rate. So by failure, I mean that we have an error beyond a certain threshold. And as we decrease the initial overlap, our method basically always succeeds. And for phase estimation, if the circuit depth is fixed, the failure rate just goes up. And if we want to keep the failure rate low, we will have to increase the circuit depth in quantum phase estimation. So earlier I mentioned that there is some difficulty in approximating a discontinuous function using a continuous one. So in particular, we want to approximate a Heaviside function. So here we actually have a kind of a manual construction of finite Fourier sum that approximates the Heaviside function. So this is how it looks like. So basically, you can see here, within this interval, this function takes value very close to 1, and within this interval, it takes value extremely close to 0, and there is a tangential interval in between. So, so if we want to if we want to keep the oscillation here below a certain threshold epsilon prime, the degree will scale like a delta inverse times log delta inverse times epsilon prime inverse. So you can see the scaling with respect to this epsilon prime is actually very good. So there is a later work that improved this construction. I'll talk about that work later. So, and this is opposed to taking a naive approach of, say, truncating the Fourier expansion of the Heaviside function. So this might be the first thing people think of when approaching this problem. And if we just truncate the Fourier expansion, this is the kind of approximation we will get. So basically, in the interior of this interval, the approximation can be fine, but when it's close to those jump discontinuities, we will see this kind of oscillation. And actually, the oscillation doesn't decrease as you increase the number of terms in your approximation. And this is known as the Gibbs phenomenon in the applied math setting. So this will basically ruin your algorithm, and therefore we have to have this kind of finer construction, which we propose in our work. And so far, we have been focusing on like reducing the number of ancilla qubits and reducing the circuit depth requirement. But in actual implementation, we might want to avoid running controlled time evolution. And controlled time evolution is actually needed in the original version of our algorithm. This is because, like, imagine you can design a quantum circuit for performing this time evolution, and the most simple way to do control time evolution will be just to replace all the gates by the controlled gates. And this will actually give you a pretty large overhead in actual implementation. Therefore, we consider whether it would be possible to remove controlled time evolution altogether. So here we use an idea proposed in the following two papers. And basically, we assume we have a reference eigenstate psi r that is easy to prepare and corresponds to a known eigenvalue. Once we have such a reference state, we can use this kind of two ancilla qubit circuit to run actually the same algorithm. But here, as you can see, we no longer need controlled time evolution, but we will need controlled state preparation instead. So we will need to prepare both the initial guess and the reference eigenstate in a controlled manner. And so this kind of reference eigenstate is generically not easy to find, but if we restrict ourselves to the quantum chemistry case where we have particle number conservation, one candidate is readily available, which is the vacuum state. So yeah, so this is actually really nice for the quantum chemistry setting. And so far we have been only looking at the ground state energy. Some later works extended our framework to include estimating the observable expectation values as well. And also we haven't discussed the issue of implementing the time evolution operator into the -IHT in our work. And in this recent work by Juan Berta and Campbell, they designed a method to perform unbiased estimation of these things with cost that is independent of the number of terms in the Hamiltonian. But this can be pretty advantageous if the Hamiltonian involves a lot of terms and your circuit depth is kind of restricted. So to summarize, we developed an algorithm for ground state energy estimation that has the following features. First, it achieves the Heisenberg-limited precision scaling, and it uses few ancilla qubits, so 1 for controlled version, 2 for control-free version, and it also requires shorter circuit depths than quantum phase estimation. And besides the ground state energy, our algorithm actually can output the cumulative distribution function, which could be of use in itself. So the exact CDF will basically tell you everything you would want to know about the spectrum. However, here we only compute the approximation to it, so the information we can extract from it is limited. However, this is still some very useful thing to have. And our method is actually a general method to evaluate quantities of this form, so trace rho times f of x minus tau h. So in some sense, you can view this whole thing as a convolution with the spectral measure. So this works for any given 2-pi periodic smooth function. And actually, you can do it to get things beyond the CDF. You can actually compute the probability distribution function. And this is kind of similar to what Soma considered in his 2019 paper. So yeah, so we anticipate that this is actually a pretty flexible framework, and we'll be able to do more interesting things with this framework. With this, I want to thank you for your attention, and I'm happy to take questions.